Welcome to the Explainer. Today, we're going to tackle a concept that you probably use every single day without even thinking about it: velocity. But as you're about to see, it's so much more than just speed. We're going to unpack that difference and look at how we measure it, from the big picture view of a whole trip all the way down to a single tiny moment in time. So let's kick things off with a little puzzle to get our gears turning. Imagine a car driving in a perfect circle. Its speedometer is locked dead on at 20 miles per hour. So is its velocity constant? Now the answer here, it's probably not what you're thinking, but stick with me and by the end of this, you'll know exactly why. Okay, let's dive in. Okay, so to even start to crack that puzzle, we've got to get super clear on our terms. In day-to-day life, we throw around words like distance and speed pretty loosely, right? But in physics, they have very specific meanings, and getting them right is the key to truly understanding velocity. All right, first up, distance versus displacement. Let's say you walk 10 meters forward, then you turn right around and walk 7 meters back. The total distance you've walked is 17 meters. Simple enough? That's a scalar quantity. It's just a number. But what's your displacement? Well, that's just the straight line from where you started to where you ended. You're only 3 meters from your starting point. That's a vector. It's got a number and a direction. And you know, this exact same idea applies to speed and velocity. Speed is just how fast you're going, your total distance divided by time. It's a scalar. But velocity is your displacement divided by time. It's all about how your position is changing. So here's the absolute key. Velocity is just speed, but with the critical addition of direction. And boom, right there, that's the answer to our little puzzle from the beginning. That car driving in a circle? Yeah, it has a constant speed, 20 miles per hour, for sure. But because it's constantly turning, its direction is always changing. And if the direction is changing, well, then the velocity is changing. So nope, its velocity is absolutely not constant. Okay, let's get a little more technical for a sec. In physics, velocity is defined by this thing called a dimensional formula. Now, I know m0, L1, t -1 looks a little intense, but it's just a fancy way of saying velocity is all about length divided by time. The m for mass is raised to the power of 0, which is just a way of saying an object's mass has literally no effect on its velocity.
Kind of cool, right?
So now that we've got a handle on what velocity actually is, let's talk about the two main ways things can move. And believe me, this distinction is everything when it comes to understanding motion in the real world. On one hand, you've got uniform motion. This is perfect idealized motion, where an object has a totally constant velocity, meaning its speed and its direction never ever change. Think of a satellite cruising through deep space. But here on Earth, pretty much everything experiences non-uniform motion, where the velocity is always changing because of things like friction and air resistance. Yeah, when you think about it, almost everything you see is non-uniform motion. A car taking off from a red light, a ball rolling faster and faster down a hill, even just you walking through a busy street, your velocity is constantly in flux. And that brings up a really interesting problem. If the velocity isn't constant, how in the world do we measure it? To deal with a messy journey full of starts, stops, and turns, we need a way to see the big picture, to kind of smooth out all those little changes. And the tool we use for that is called average velocity. Think of it like a long road trip. You speed up on the highway, you slow down for traffic, you stop for gas. Your speed is all over the place. But your average velocity doesn't care about any of that. It only looks at two things: your total displacement, where did you start versus where did you end, and your total travel time. That's it. It boils the entire trip down to a single, simple value. And the formula is just as refreshingly simple as the idea. You see that little triangle symbol? That's the Greek letter delta. And whenever you see it in physics, it just means change in. So average velocity is simply the change in your position divided by the change in time. Okay, but the big picture isn't always what you need, right? What if you don't care about the whole trip? What if you want to know your velocity right now, at this very second? Well, for that, we need a completely different tool, one that's much more precise. And that tool is instantaneous velocity. It's not about the journey, it's about a single snapshot in time. You already know this one. It's that moment you glance down at your car's speedometer. That number you see is your instantaneous speed, and the direction you're pointing your car, well, that's the other half of your instantaneous velocity. Okay, now don't let the formula on this slide scare you. The idea behind it is actually pretty cool and intuitive. What we're doing is taking our average velocity formula, that change in position over change in time, and we're shrinking that change in time, that delta t, making it smaller and smaller and smaller until it's practically zero. This dr/dt thing, that's the language of calculus, and it's just the super precise way of describing the rate of change at one exact instant. So in practice, how do you actually find this? Well, it's basically like following a recipe. First, you need an equation that describes an object's position over time. Then you use a tool from calculus called a derivative to turn that into a new equation for velocity. And finally, you just plug in whatever moment in time you're curious about and boom, out pops the exact velocity for that instant. All right, last section. Let's pull all these ideas together and see how they all connect and play off each other. And look, we're right back to our most fundamental distinction. Instantaneous speed is simply the magnitude or the size of the instantaneous velocity. One is a scalar, just a number. The other is a vector, a number, and a direction. It's the difference between saying you're going 50 miles per hour and saying you're going 50 miles per hour heading north. So, here's a great question that really ties our two main ideas together. When does the big picture of your whole journey perfectly match the snapshot at any given moment? The answer? It's pretty simple, actually. They are only the same during perfect uniform motion. If an object's velocity never ever changes, if it's always moving at the exact same speed in the exact same direction, then of course its velocity at any given instant is going to be the same as its average velocity for the whole trip. All right, let's do a quick recap. We started with a tricky question about a car and ended up with a powerful way to describe motion. Just remember, velocity is speed plus direction. Real-world motion is almost always non-uniform, which is why we need two tools: average velocity for the big picture and instantaneous velocity to zoom in on a single moment. And that really brings us to the next big question. We figured out that velocity is the rate of change of position. So what's the next step? Well, it's acceleration, which is the rate of change of velocity. Based on everything we've talked about today, what do you think that looks like for a car, starting, stopping, and turning through a city? Something to chew on. Thanks for joining me.